Since we haven't been meeting in class the way we normally hold this class, and since I can't see you face to face and I don't have a lot of papers to take up and review, that I may be taken for granted that you are internalizing the basics. So, what I want to do today is simply go back and do a comprehensive review up through chapter 6, and then I'm going to add 7 and 8. So, I sent this file to you just before class today. So when you get it, I need for you to print it so that you can fill it in and you have everything that you need to have a good background in this course. So let's begin with the first one, okay? Please go into chat and see who knows number one exactly how we're supposed to be using it. Number one. So I'm going to go in chat and see who can fill out number one very quickly. Okay, Nigel, very good. Okay, anyone else? Knows answer to number one? Keston, very good. Anyone else? Okay, I see I have Lanisha in class today. I see I have, okay, Lanisha's answered. Okay, I see Kaylin is in class, Kendra's in class. Okay, so I'm waiting to see if everyone can fill that one out. Okay, so I'm not hearing from the others. Now, this is very important because we're not able to convert readily between the units if we don't know our most basic conversion. So in order for us to get the same answer each time, we must use the same numbers. So for us in this class, when we convert between meters and feet, we're going to use 3.281 feet. That's the number we have to all use. Okay. What about number 2? Go into chat and give me the answer to number 2. Okay, very good. Alex, Lanisha, Kaylin. Okay, very good. Okay. Okay. Let's go in, Keston, very good. Okay, 1 hour, how many seconds? Okay, very good. Now we can say 3,600 seconds, or we can say 3.6 kiloseconds. We can say that because we know that we can write it in scientific notation or using one of our SI prefixes. Okay, what about 1 day? How about 1 day? Go to the chat and put in 1 day. Okay, Kaylin has it correct. Nigel has it correct. Keston has it incorrect. Look at it again, Keston, because all we're doing now is multiplying this number by 24. 24 hours in a day, 3,600 seconds in 1 hour. So we should get 8.64 times 10 to the fourth seconds. Okay. How about number 5? If you have 1,000 meters, you have what? That's a very easy one there. 1,000 meters is, okay, very good. Very good, Keston. Okay, now you have 1 gram. Okay, if you have 1,000 meters, because 10 to the third means kilo, you have 1 kilometer. Okay, how about 1 gram? How many kilograms is that? You have 1 gram. Okay, number 6. You have only 1 gram. How many kilograms is that? No one? Okay, very good. Okay, so kilo we know means 1,000, but we only have 1, so we have 1,000th, and we should write that as 10 to the minus 3. In other words, if it takes 1,000 meters to make 1 kilometer, if I only have, say, 1 meter, I would have 1,000th of a kilometer. Or if I only have 1 gram, I have 1,000th of a kilogram. So this is to remind you that this negative exponent is actually a way of writing a fraction. In other words, 10 to the minus 3, which we know is 0.001, which is 1,000th, is actually 1 over 1,000, which is 1 over 10 to the third. But of course, when this comes up from the denominator to the numerator, it becomes negative. So I want to make sure that you know that well. Okay, and then last time we learned that 1 horsepower is 746 watts. Okay, now I want to use this problem to go, what we've learned just right here, to go and solve one of the problems that you all did not get in the midterm. And you'll see a very similar problem when we do the final exam. So give me a moment to pull this up. Give me one moment. Okay, I'm not going to be able to pull it up on the actual, on the actual, um, I'm not going to be able to show the actual problem, but I am going to be able to put it on the screen. So what I'm going to do then is just go to my screen and show you how to solve this problem and what I was wanting you to do in this problem. Okay, so let's go to the whiteboard. Okay, so in the exam, I asked a simple question, which I thought was a simple question, but let's see what you think about it. I said that how long would it take for, at the rate of 2.8, I think it was nanometers per second. And of course, that was my speed. How long would it take at the speed of 2.8 nanometers? I want the time to be in years. If I wanted to grow a length of, and of course, this is my distance of, I think it was 0.28 meters. And I think in the exam, this is written as 28 centimeters. Okay, so two things here. First of all, I want you to quickly identify the equation. Secondly, I want you to know your SI prefixes. So maybe in the next comprehensive exam, I will include a list of your SI prefixes so that in the next exam, you will have that also written out. But here, quickly, let's solve this. Time is distance over speed. Now, the distance is 2.8 times 10 to the minus 1 meters. You see, I chose to write that this way because I'm choosing to write it in scientific notation. That's so important. It makes the problem so much easier to solve. And that's preferable. So in this lesson, I hope you're watching these little nuggets that I'm trying to show you. Okay, divided by the speed. And the speed is 2.8 times 10 to the minus 9, because nano means minus 9 meters per second. So that, I'm telling you again, when you divide by a fraction, then the denominator in the fraction moves to the numerator. So therefore, and you should see how that has to work out, because I'm looking for time. So that means that every other unit has to cancel out, and the only unit that remains has to be a unit for time. So that's what happens here. Now, 2.8 and 2.8, of course, will cancel. So that's just 1. So now I have 10 to the 8th, because see, this is minus 9, but when it comes to the numerator, it becomes a positive 9, and a positive 9 plus a negative 1 will give me a positive 8. Now this is now seconds. But I want the answer to be in years, because no one gives a time in 10 to the 8th seconds. That's 100 million seconds. No one gives an answer like that. Okay. Or I should say that's 1,000 million. Okay, so let's go ahead now and, no, 100 million. Okay, let's go ahead now and convert this. So that means then that I need to be able to know quickly how to go from seconds into hours and hours into days and days into years. And of course, that's such an easy conversion. That's something we all should know. So now we know that it takes what? 3,600, or you can put it how you want to, 3,600, or I can say 3.6 times 10 to third seconds to make 1 hour. Okay. We know that there are 24 hours in one day, and there are 365 or so days in 1 year. So I pulled this problem up because a problem like this is similar to what you have to know to understand what we learned in chapter 1, which is the chain link conversion method. Okay, the chain link conversion method. So now, someone quickly, you see seconds will cancel, hours will cancel, days will cancel, and the only unit remaining is years. So now, in your calculator, if you don't have it, go get your calculator and give me this answer. What is this answer in years? So I'll go to okay, Kaylin can't hear. Let me see. Um, okay, great. All right. Okay. So I think it's about 3 years. I can't remember exactly, but I see an answer here. I see another answer here. So who's having difficulty getting this answer? Is anyone having difficulty getting this answer? Okay. Lex, that's good. Okay, so if you get about three years here or so, that means that you understand the chain link conversion method. Now, the chain link conversion method, this is just a standard. I gave you time in this example because time is so easy to do. But of course, we can do this for speed. We can do this for length. We can do this for weight. We can do this for any unit. But this problem was chosen just to make sure you understand the standard way to write the chain link conversion method. And that's one of the topics from chapter 1. Okay. Now, also, I'm reviewing this part of what we've covered today. So when I do the next part of the review before the final, make sure you know I've already covered this. I won't be covering this part again, but I may be covering, say, chapters 6, 7, 8. I think we're going to do chapters 11 and 12. Okay. Any questions? Okay, let's go back to our okay. So unfortunately, when we leave this sheet and come back, um, everything we have written is gone, but that's just what it's like. Okay, so let's go back to completing this equation quiz. Okay, so what is this combination of units? First of all, we know that we have 3 basic units. For mass, we use the kilogram. For time, we use the seconds. For length, we use the meters. Now, what I want you to see is that everything we're going to discuss from this point on is based on these 3 basic units. These are the basic SI units. So then we have intermediate in SI units. So intermediate means that these are derived units, okay? Or I can call these, I think I'd rather call these derived units. Derived in SI. See, intermediate means that I'm going from my basic to the combination, and then I get my derived unit. So I can say intermediate and derived. All right. Now, what is the kilogram meter per second squared? What do we call that unit? Let's see what somebody has said. Okay, very good. We call it the Newton. All right, very good. That's the Newton. Now, the Newton is the unit for what 3 things can we think of when we think about, I'll just say 2 maybe. What 2 things we think of when we think about the Newton? When I say it's measured in newtons, what comes to your mind? Go to chat and tell me, what would you measure newtons in? What quantity? Okay. What quantity would you use? Okay, force and weight. Very good. Okay, force and weight. All right. Now we have another unit. We use these 2, Newton meter, and we come up with another derived unit. And what is Newton meter called? Okay, let's see what somebody's saying. Okay, very good. So the Newton meter, we call that the joule. Okay, call that the joule. And that is the unit for what 2 basic quantities. Okay, we said the Newton is for force and weight. And we use the joule for work and energy. Okay. And then finally, someone tell me, what is a joule per second? What is a joule per second? Okay, very good. Alex told me this is the unit watt. Okay, and what do we measure with the watt? What do we measure with the watt? Anybody? Very good, Kaylin. Thank you. We measure power. Okay, so what I want to show you with this quick review is that these quantities have to make sense to you so that when you solve the problem and you identify what's given in the problem, then you will know that you are working toward one of these quantities. So in the physical sciences, even after we have understood the physics, we have to be able to use basic algebra and a little bit of trig to solve these basic problems. So let me go here and show you what else I want you to do. We may not do it all today, but I'm going to show you what I put on this particular. Okay, let me clear. Okay. So let's go here, okay? So this one says, how much over the posted speed of 25 miles per hour are you traveling if your speed is 15 meters per second? So see, we have mixed units here. So what are we going to do first right here? Okay. How much over the posted speed of 25 miles per hour are you traveling if your speed is 15 meters per second? So the posted speed is 25 miles per hour. So your answer then should be an answer in so many miles per hour over, because that's what's posted. But it says you're traveling, so it gave you your speed in 15 meters per second. So the first thing you got to do is what? Tell me what you got to do, someone. Okay, someone, what you going to do first in this problem? Write your answer, please. Okay, Kaylin, that's part of it. Okay, that's part of it. Kaylin is on the right track, but that's not complete. Okay, very good. All right. So that means then that you have to be able to understand how to use a chain link conversion quickly. So in this case, you're going to take your 15 meters per second, okay? And you see now, you can use this chain link conversion to do more than one unit on this one chain. So I don't want my unit to be seconds. I want it to be hours. I don't want my unit to be meters. I want it to be miles. So I say, well, and we just did this, 1 hour is 3.6 kiloseconds, and 1 mile is 1.609 kilometers. Now, if we do it that way, look what happens. Seconds and seconds will cancel. Meters and meters will cancel. And kilo will cancel. So my answer then will only be in miles per hour. And if I do it like that quickly, after doing it so many times, if I'm in an exam, I'm going to remember after some point that I'm going to multiply by 3.6 and divide by 1.609. But it takes you doing the problems a few times for you to get that. Okay. So in this review, I'm trying to put several things into one problem so that hopefully you will see that doing a sheet like this is going to be advantageous. Okay, so I got 15 times 3.6, divide that by 1.609. Okay, so if you were doing that problem, you were doing an exam, you would get 33 point, I'm going to say 33.6 or approximately 34 miles per hour. So the question says, how much over the posted speed of 25 miles per hour are you traveling? So we say this is about 34 miles per hour. Then of course you're going 9 miles per hour over the posted speed. So what is my point here? My point here is that by this point, by this time in our course, this kind of thing has to come sort of second nature. And if not, at least be able to write it down quickly by knowing your conversions. Okay. Any questions? All right. Let's go to number 69. Okay. Answer that question for me. How long does it take a penny, gave you the mass, to fall from the Sears Tower? Okay, 1,730 feet. How long does it take? Well, before I do that problem, though, let me go back up to our equation quiz. Some of our questions that you need to know. Okay, let me go back up to the equation quiz. Okay, right here. So before we even started doing any real physics, we discussed basic equations. So we said, what is average speed? We said average speed then, and we used the symbol V without an arrow on top. And we define that as distance over time. And because this is a scalar, we don't put a vector here. And of course, we measure all distance in meters, measure all time in seconds. Then we said average velocity. Now velocity, we put an arrow on top because we said velocity has both magnitude and direction. So remember, our example was the problem where we said, okay, say you go 3 miles this way and then 4 miles this way. So you've walked 7 miles. All right. If you walk 7 miles, your distance is 7 miles. That's your distance. But we learned that the displacement, okay, we have to use Pythagorean theorem, and displacement here is not 7 miles, okay? Okay, the displacement is 5 miles, exactly. Now, I want to pull up this picture real quickly because this also, and I'm moving ahead now, but this is also the 3, 4, 5 triangle that I want you to use in all of the chapters that's going to continue. And if you notice in the midterm exam, I used this equation, this triangle quite a bit, as well as the 45, 45, 90, as well as the 30, 60, 90. So please make sure that you know the 3 triangles that I've emphasized in this chapter. And the 3, 4, 5 is just one of them. So displacement, so right here, I would write this as just a regular D. This is a regular T, because time, of course, is a scalar. But here, I would put an arrow on top. So that means that this distance is 7 meters, but this displacement is 5 meters. So make sure you understand the difference in those two. Then we said average acceleration. And we simply defined acceleration as the change in speed or the change in velocity over time. And we use the symbol delta to always mean change. So change in speed over time, and we define that change as V final minus V initial over time. And we know that speed is in meters per second. So we have meters per second, and we said that is meters per second squared. So I'm going through this now because I'm trying to explain to you how imperative it is for you to know these basic quantities. You have to know these. So if you notice now, these units, we didn't call them a new name. So they're intermediate units that define these quantities. Then in chapter 2, we went over the kinematic equations. Okay, so I'm going to go to chat, see if you can remember these. If after I get the first one down, I'm going to call it out, and I'm going to say you can't give me that one again. So number 17, give me one of the kinematic equations. Someone. One of the kinematic. Okay. Okay. So let me write these down quickly so I can get them repeat. Okay. Well, I have this one. So we said that V final is V initial plus AT. And of course, if it's V final, it's in meters per second. So look, okay, so Nigel gave me that one, and Lanisha gave me that one. Okay, very good. Now, Kaylin has given me another one. Kaylin and Keston has given me another one. So that tells me that when we talk about distance in our kinematic equations, we don't use D, we use X, because X is along the horizontal. So Keston and Kaylin says V initial times time plus 1/2 AT squared. And we're looking for distance. Okay, I need two more. These are my kinematic equations. Nigel, Kaylin, Lanisha, and Keston are good participants. And also, let me tell you this, class, I'm trying to keep notes, and I am keeping notes of who's responding in class. This is your extra credit points. Okay, Kaylin and Lex have given me another one. Okay, give me a minute to write it down. So V final squared is V initial squared plus 2AX. This is meters per second to be squared. So let me stop right there for 1 minute and show you something. If this unit is in meters per second, that means that this term is in meters per second and this term is in meters per second. When I add them together, I get meters per second. That means that this term is in meters. This term is in meters. I add them together, I get meters. This term is in meters per second, the whole thing squared, and the same here. So make sure you understand that these units have to be correct as well. All right, and then my last equation is displacement is 1/2 V initial plus V final times time. And of course, we're back to what? Meters. Okay, now, class, you need to have these really understood. And I'm saying that now because I'm going to do chapter 8 on Wednesday. And if you don't know the kinematic equations for linear motion in one dimension, you're going to have difficulty with chapter 8. So I'm reviewing this again so that you will know what is required of you in order to do well. So good, we know these. All right, very good. Let us move now to that problem that I was talking about earlier. Well, no, one other thing first. Okay. Okay, right here. Free fall from rest. So that equation that we had last, we said that, well, we had this equation, not last, but we had this equation. X is V initial times time plus 1/2 AT squared. Now, when an object falls from rest, we have already determined how we're going to approach this problem. And the convention and the rule is that the initial velocity is 0. And it falls under acceleration due to gravity. And that magnitude of g, the positive part of that is 9.8 meters per second squared. So that means then that height, so my displacement now is the height, and VI is 0, so this whole term is gone. And that is 1/2, and A, I'm going to use G, T squared. So whenever an object falls freely from rest, we're looking for its height. We have a very simple equation. H is 1/2 GT squared. Now, we know that this value for G has two values. We have the value for the SI. We have the value for the US customary system unit. So what is the value for G when it's not in the US? I mean, when it's not in SI, when it is in US, what is the value for G? Someone put that in for me. Okay. Nigel, I need the whole thing. Okay, the value for G. You're close, Nigel, but it's not complete. Okay, very good. You see, we have to have the right units. Okay, so it's 32 feet per second squared. Okay, very good. Very good, Kaylin. All right, very good. So now let's go to that problem I was talking about earlier. Okay. Okay, here we go. So let's look at number 69. How long does it take a penny to fall from the Sears Tower? So if it's falling, we know that the initial velocity is 0. We have the height. It says ignore air resistance. I'm looking for time. Who can solve that problem very quickly? First of all, put in what's the equation you're going to use? Not only the equation, once you rearrange the equation, show me how you're going to write that that equation on your paper. You're solving for time. How are you going to write that equation out? Which equation you're going to start with and how you're going to write it out? How you're going to rearrange it because you're looking for time. No one? Well, first of all, give me the equation you're going to use to solve for time. In other words, your clue is to start with the given. Okay, you start with your given. What you're given is the height. The Sears Tower, its height. So you're given feet. Okay. Okay, very good. Nigel, very good. Okay. So once you're given the height, the object is falling, you know it's falling under the influence of gravity. So then you know what you have to use G. but which G are you going to use? Well, because I'm given feet in this problem, don't be, uh, don't think that I need to convert this into meters. And the reason is because how long is time? And time is a quantity that is the same if I measure in feet per second or meters per second. Time is a quantity like that. So once you understand that, you won't first try to convert this into meters. It's an extra step that you won't do on the final exam. You'll quickly say, okay, well, if I know a value for G, which I do know, I'll use it. Okay. Then I'm going to solve for time. So my original equation that I know is height is 1/2 g t squared. I'm looking for t. So I need to take the square root of something. Okay, the square root of what? Well, once I get t by itself, that means I multiply both sides by 2. I've divided both sides by g. So now I have this, but I need to get what? The square root. And once I do that, it's easy now for me to plug in these numbers to get my answer. So I have 2 times, what is h? 1730, and this is feet, divided by 32 feet per, see right here, I want to put per second square, but because I know that this quantity, this unit, has to go to the numerator. And therefore, when I take the square root of this answer and the square root of this unit, my answer will be in so many seconds. You see? That's how beautiful it is. It makes so much sense. And of course, here my feet will cancel out. So let's see what we get. We got 1730 times 2. And that gave me that, and divide that by 32. Okay. And I get, let me see, let's say 1730, yes. Okay, I get that, and then I say second function square root, second function answer, and I get 10.39. Okay, very good. Okay, Keston and Kaylin, very good. So my time is 10.4 seconds. This object is falling. Now, the next question is, what is the impact speed? And, well, I'm not going to do momentum. I haven't gotten that far yet, but I'll change this to kinetic energy for a reason. Because this momentum is what we're going to cover in the next chapter. But because we haven't gotten there yet, I'm going to change it to kinetic energy. So what is the impact speed? That question is asking you, what is the speed that the object will have once it hits the ground? Okay. Who can give me that number? And the answer could be in SI units, or the answer can be in, okay, give me the answer in SI units. What is the impact speed? Give me the answer in SI units. So this would be meters per second. Okay, anybody has the answer? What is the speed, the impact speed? When this penny hits the ground, how fast is it going? Okay, very good. 101.9, okay. 101.9 meters per second. Okay, very good. 101.9 meters per second. That was Nigel. Okay, now, quickly, someone, this is back to conversion, just to get an idea what's going on with this. How many miles per hour is that? In other words, by the time that penny hits the ground, falling from the Sears Tower, about how many miles per hour is it moving? Okay, so we have 101.9 meters per second. So we don't want meters per second. Now we want miles per hour. Okay, this is how many miles per hour. So now we know what to do very quickly, don't we? We know how to convert between meters and miles and seconds and hours. But look what happens this time. Before we said we're going to multiply by 3.6 and divide by 1.609. But look what happens this time, okay? 1 mile is 1.609 kilometers, and 1 hour is what we have, 3.6 kiloseconds. We want to get rid of the meters and go into miles. We want to get rid of the seconds and go into hours. Oh, okay, this is what we did before, okay. So meters and meters cancel, seconds and seconds cancel, kilo and kilo cancel. And what do we get? How many miles per hour? Anyone? Very good, Alex. Okay, 228 miles per hour. Who would imagine? Would you have thought that that penny was moving that fast? You probably would not have thought that penny was moving at 228 miles per hour. So when I ask you later on for the momentum, that's not in this question, but later on we'll solve it that way. But right now, let's do the kinetic energy. How much energy has this penny picked up falling from the Sears Tower? Okay, so let's go back to our other equations now. I hope that you can see how all of this builds and how all of this has a role in your mastering this course. You have to build from the most basic concepts to these more advanced concepts. But they're not so advanced if we sort of use, like say, climb the ladder successfully, one rung at a time. Okay. Okay. So then we went to chapter 2. I'm sorry, chapter 3. So all of that is just a way for us to put on one page the basic understanding that we've learned in just the first 2 chapters. So now we go to this page and we're going to begin learning chapter 2. I'm sorry, I keep saying 2, 3. All right. So refer to this figure. You're given the initial velocity. So of course the author uses the symbol subscript 0, but we use I, but it's the same thing. So the initial velocity the initial velocity here is 25 meters per second. And I want to know what is its initial vertical velocity. Okay, that means what is the initial velocity on the y-axis, because vertical means up and down, whereas the initial velocity on the x-axis is my horizontal. Okay, so someone give me those answers quickly. And of course, this picture tells me that I have to use my understanding of trig functions because I'm given the angle theta. That's my clue then to solve for VIY and VIX. Okay, give me those two answers quickly. Okay, I have an answer for uh, uh, Nigel. That was good. For let's see, only Nigel answering the question. VIY and VIX. Okay. Keston, look at your VIX again. Okay. Okay. Okay, very good. So if we put in our, so let's just look at this one more time. Of course, this is Pythagorean theorem. That's one of the things that we have on this sheet as well. I thought I had it up here earlier. So let me go and go here real quickly. Let me go down to where this is on your, I thought I had Pythagorean, I thought, oh, here it is right here, this one. Okay, number 48. So from that picture that we just had, we know that this represents my initial velocity. But we said that initial velocity has a component in x that takes it horizontally, and it has a component in y that takes it vertically. So again, this is my right triangle, and we know from our trig functions that sine of theta equals opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse, and tangent of theta is opposite over adjacent. So now, from this point on, I want you to recognize that the opposite side is always the hypotenuse times the sine of theta. The adjacent side is always the hypotenuse times the cosine of theta. So that means that in these problems going forward, you don't have to do a whole lot of work rearranging these equations because it's clear now that this is going to be the exact way that you're going to solve for the vertical and horizontal component. Okay. Okay, so the initial vertical velocity, we said is going to be V initial in Y, which is V initial sine of theta. Now, I think you all solved that out. And what was the answer for sine of theta? Did y'all get 14, 14.3? What did it say, 14? Okay, 14 meters per second. And then for here, V initial in X will always be V initial cosine of theta, and that's about 20, I think. About 20 meters per second. Okay, let's just use these numbers now. So the question says the maximum height the ball attains. So that means I'm looking for the maximum height. How do we solve that problem? Well, remember, and this is something I want to point out right here, so listen very carefully. One thing that we discussed, and I want you to have it in your mind firmly, that the motion that occurs in the vertical direction occurs that way, and we can completely ignore the motion in the horizontal and vice versa. So that means then I'm going to compute the maximum height. I'm going to completely ignore the motion that's happening along the X. So in other words, in my mind, what goes up, which is vertical, must come down. What goes up must come down. But because it does have X motion as well, it doesn't go straight up like this, but it still goes up. And we know that when it goes straight up, initial velocity at the very top, the final velocity is 0. Well, the same thing happens on this problem, but because we know it's still moving, all of this velocity is not 0, but a portion of it is. And the portion that is 0 is only on the y-axis. So therefore, we say the final velocity in y is 0. So in this problem here, to find the height, which is of course on the y-axis, what is the height on that's the y? We are going to be discussing, using only the y components. So now, what do we know? We know the initial velocity in y. We know the final velocity in y at maximum height at this point. And we know that it's under the influence of gravity, which is a sub y and we call that G. And because this number is height, it's going to be a positive answer. But let's just solve it to make sure. Because in these problems, we are talking about vectors. So for that reason, we're going to say this is negative 9.8 meters per second squared. The final in y is 0. The initial in y was 14. And we're looking for the maximum height, h. So because we have gone over our kinematic equations, and because we know how to see them and quickly be able to rearrange them to solve for height, someone tell me what is going to be my equation for height. I mean, when you give me this answer right here, what is my equation for solving for height? Okay, now this is a good answer that I got from Keston, 1/2 AT squared. It's a good answer, but that would mean I've got to, okay, a good answer from Alex as well, but that would mean, class, I've got to go through another step and solve for time, which I can do. I can solve for time. You're absolutely correct. If I know V final, V initial, and acceleration, I can solve for time. That is absolutely correct. But the reason why, well, let's just go ahead and do it. Let's go ahead and solve for time. So what's my time? How much time it takes to get to the top? Okay. How much time it takes to get to the top? And then once I find that time, then I'll be able to nobody has a time yet? And in an exam, this will be taking you too long. How much time it takes to get to the top? Okay, so we know that acceleration is change in speed over time, and this implies that time is change in speed over acceleration, right? So it goes from 14 to 0. So the change then is going to be minus 14 meters per second. Acceleration is going to be 9.8 meters per second square. Meters and meters are canceled. Second cancel one of those. So my time then would be about what? 1.4 seconds. Okay, very good. My time is 1.4 seconds. So now we can use that equation to solve for maximum height. So now we can solve for maximum height. 1/2 gt squared. So what is my height? One half gt squared. So you got 1.4 squared times 9.8, and take a half of that. And what do we get for the height, maximum height? 1.4 squared. Okay. times 9.8 and divide that by 2. Okay, so Lex says it's 10. Kaylin says it's 9.6. Anyone else? Keston says 9.6. Okay, so very good. We'll go with 9.6. Okay, so the maximum height is 9.6 meters. Now, class, I want to give a shout out to Kaylin for giving me a better equation. Although she didn't rearrange it, she gave me that equation. So remember, you have a kinematic equation that says V final squared is V initial squared plus 2A, in this case, Y. Which means then I can find this Y in one step as opposed to 2 steps. So I can find this Y by simply saying that my Y is going to be what? Negative 2V initial squared divided by 2, in this case, 2G. I can do it in one step as opposed to having to do 2 steps. Okay, and of course this G in this case is negative, so my whole answer is going to be positive, which is going to be good. So what we get this time? Solve that one, see what you get. You got V initial in Y, which is 14. You got 14 squared times 2. Oh, I'm sorry. What should I not have right here, class? Shouldn't have this 2 right here. Not that 2. Okay. V initial squared divide 2G. And what do you get this time? You got 14 squared divide 2 divide G. No one? Is the answer not correct? Let me see what I get. Okay, are you all saying VI, which is 14? Are you squaring 14 and then dividing it by 2 and then dividing it by 9.8? So looking at these numbers, I don't see why you're getting these numbers.
Mine was because I multiplied by 9.8, not divided.
Okay. All right, we have to do it correctly. I'm still looking for the right answer. They got VI squared, and VI was 14 point something. I can't remember what it was now. We just said 14 divided by 2. Okay, Alex, very good. You should get about 10 because we said earlier 9.6, which is approximately 10 meters. So we do it this way, we still should get 10 meters. We use the exact numbers here, we probably would get a little different answer, but this is good. Now,
I'm not getting that answer. I keep getting 960.
okay, so take 14 and square it.
Yeah, that's because you were multiplying the G instead of dividing the G, that's why.
Okay, so right here, G is being divided. This is divided by 2G, you see? It came from this equation. We're looking for Y. So that means then in this equation, we have 2AY is V final squared minus V initial squared, right? From this equation. But of course, V final squared is 0. So we're going to have negative V initial in Y. And we're going to divide that by 2A. And of course, A is going to be the value of G. So we're going to have 2 this whole, well, I'll just put this negative 9.8 meters per second square. That's what happens. So that's in the denominator, see? The G is down here.
Yes, I mean, I get that. I'm still not getting 10.
Okay. So you put in 14 squared, got 196, right?
Right.
Okay, you got 196. Now you divide by 2. What do you get?
98.
And you divide by 10. I mean, you divide by 9.8. What do you get?
Okay, I got it.
Okay, so that brings up a good point. I'm glad you said that, because that's something that I think that a lot of students still have a misconception about. You see, this G is in the denominator, which means that once I square this number, everything down here is being divided. You don't come back and multiply by the G. Now you could, of course, do it separately. You could say VI squared and get 196. And you could say 2 times G and get 19.6. You can do that. And then you would get, of course, 10, right? But that proves then that once you get in the denominator, that you do not multiply, because this number right here is also being divided by this quantity. So I think that was the problem that you all had initially. Alex and Kaylin and someone who was speaking, that's the problem that you were having. And I see that problem comes up a lot. And that's why I intentionally put sometimes the wrong answer to see if you know how to do the algebra. And the algebra means that this division means everything in the denominator is being divided, and you do not go back to multiplying. But you can multiply first now and then divide. You can do that. Is that clear now?
Yes, ma'am. I was squaring my G and not multiplying it by 2. That was
Okay.
my problem.
All right. Okay, now to find the range. So it's 2:51. Time is extended beyond by 6 minutes already. So we'll start there tomorrow. I may not do as much on this page, so I need for you as your homework to go ahead and complete the rest of this equation quiz. And if you have any questions, I need for you to ask me in the first part of the lecture tomorrow. Because if you can notice here, you see I have all of this that we've gone over. So once we finish the range, I want you to finish 23 all the way down to 38, because that's what we've covered. And we're going to start a new chapter with chapter 7 for potential energy and momentum. Oh no, that was in that chapter. Okay, no, finish all the way down to 43. I'm sorry. And we're going to start with impulse. I think we finished all that in chapter 5 and 6. So we're on chapter 7. Okay, so if you can finish that up, and we'll review what you don't understand. Then down here, I have some test your understanding problems that you can use to see if you understand what we've been doing so far. Okay, with that being said, please sign your name as you exit.